In the previous video, we looked at basically how to verify a solution to a system. And then we also looked at the graphing method. We saw that there were equations that have one solution, no solution, and then an infinite number of solutions, but we didn't give names to those. So let's go ahead and give some names to those sorts of systems. So any system that has at least one solution is called consistent. If a system has no solution, it's called inconsistent. If a system has an infinite number of solutions, it's called dependent, okay, because the lines are dependent upon one another. And then if it only has one or zero solutions, okay, at least with these types of linear systems, then it's going to be called independent, okay? So in the graphs below, right, this is going to be a consistent system because it has at least one solution, okay? And then it's going to be independent because it's not the exact same line. Over here, we have an inconsistent system. Okay, so notice that there are zero solutions, but it's also independent because the lines are not on top of one another. Right here, we have a consistent solution because it has at least one solution. And then it's going to be dependent because notice that the lines are on top of one another, or basically you only have one line. Now, finally, over here, this looks like it would be inconsistent, but it's not, because if I was to keep going on with this pattern, okay, eventually, okay, and I know that's not good, I apologize, but if I zoomed in a little bit, I might get a better representation of this. But if I were to draw this a little bit better, okay, and keep going out, all right, still bad, but all right, notice at some point it would intersect, okay? So sometimes the graphs don't give us the whole story. We might have to readjust our windows a little bit, okay? So this would be a consistent solution that is independent because we only have one solution, okay? Going back, remember we had one solution to this system in the previous video. And so that would be a consistent and independent or independent system. This one is an inconsistent but independent. And then finally, consistent but dependent. Right? So those are the three types of systems that we could arrive at. Okay, so I just want to make everybody aware of this terminology. So that way, if I say it throughout the videos, then we understand that inconsistent means no solutions, dependent means infinite number of solutions, etc. All right, now we've seen the graphing method. All right, and the graphing method's okay. There's nothing wrong with it, but we want to make sure that we're able to solve these sorts of systems analytically. Okay, and basically analytically means without a calculator. And so we're going to be solving by two more methods. The first of which in this video, we're going to focus on the substitution method. Now, substitution method is exactly what it sounds like. We're going to substitute one equation into the other. All right, so if an equation contains any decimals or fractions, we're going to multiply by least common denominator, okay, or an appropriate power of 10 if it's a decimal, okay? Then we're going to solve one equation for one variable. We're going to substitute the solved equation into the unused equation. And we're going to basically get an equation in one variable, and we're going to solve, and then we're going to back substitute. Okay, so for instance, we have this pretty elementary system of equations. We have y equals 2 minus x. So what I'm going to do is I'm going to take and I'm going to substitute back in here for y. Okay, and I want you to notice, by the way, that the first two steps are done for us. Okay, notice that we already have y equals. Okay, if that wasn't done, then we'd have to do a little bit of algebra to be able to finish that off. Okay, so I'm going to substitute in here. So this second equation is now going to become 3x minus the quantity of 2 minus x equals -2. I'm going to distribute, and so I get 3x minus 2 plus x equals -2. I'm going to combine like terms and get 4x minus 2 equals -2. I'm going to add 2 to both sides. 4x equals 0. I'm going to divide by 4, and we yield one solution, which is x equals 0. Right? Now, that's only half of the solutions, because now what we have to do is we have to back substitute the solved variable. And we can do that all the way back up here where we have y equals. Okay, so we would have y equals 2 minus 0, or y equals 2. And so our solution would be the ordered pair 0, comma 2. To check this, we might want to graph it, okay? And that would be my suggestion, folks, is to go through and graph this, the equations, just because it never hurts, okay? So we would have y equals 2 minus x as 1. And then for our other equation, we would have 3x minus y equals negative 2. Right? Notice that we intersect right here at 0, 2. And so it seems viable that that is going to be our solution, okay, just as a check. A second example, not so easy, okay? So we have 6x minus 3y equals 12, 9x plus 6y is equal to 15. Let's start by solving the first equation. And what I always do is I take a look at the variable that has the smaller coefficient, okay? So in this case, 3y is the smallest coefficient, okay? And I could solve either equation, it doesn't matter, but I'm just going to solve the first one. And so I'm going to subtract 6x, so 3y equals 12 minus 6x, and then I'm going to divide by 3. And so I get y equals 4 minus 2x. Now let's hold on to this because that's going to be helpful. And I'm going to substitute that all the way back down here. Okay, so I get 9x plus 6 times the quantity of 4 minus 2x equals 15. I'm going to distribute 6. Okay, so 9x plus 24 minus 12x equals 15. I'm going to combine like terms. Okay, so that's going to give me a negative 3x. And I'm going to subtract 24 from both sides. So that's going to give me a negative 9. Right? And then finally, what I'm going to do is I'm going to divide both sides by negative 3. And if I do so, I wind up with x is equal to 3. I'm going to take that number and substitute it back in, okay, all the way back where I had this definition for y. So y is going to be equal to 4 minus 2 times 3. That would be 4 minus 6, or y equals negative 2. And so our solution set is going to be the ordered pair 3, negative 2. Just because this is a little bit more rigorous system, and I'm going to stop doing this, at least in this video, is I'm going to go ahead and check the solutions for this. Okay, so in our calculator, we had 6x plus 3y equals 12, and then we had 9x plus 6y equals 15. Okay, down here, we have the point 3, negative 2, 3, negative 2. So either we got really, really, really lucky, or it's the right solution. Okay, and it is indeed the right solution for this. All right. A third example, we have 3x minus y equals 4, and then we also have 6x minus 2y is equal to 4 as well. Always pick on the equation that has the smaller coefficient, or the smallest coefficient, or the one that's closest to 0 in this case. So that's going to be negative y. I'm going to start by subtracting 3x from both sides. So negative y equals 4 minus 3x. And then I'm going to divide by negative 1. And so that's going to yield y equals negative 4 plus 3x. And I'm going to substitute this back in for y down here. We would get 6x minus 2 times the quantity of negative 4 plus 3x equals 4. I would distribute the negative 2, right? So I would get 6x plus 8 minus 6x is equal to 4. I combine like terms, and when I can't combine the like terms, they cancel out. And I get the statement that 8 equals 4, right? Well, we know in mathematics that that's called a contradiction. And what this means is that there is no solution. Okay, so in other words, we have an inconsistent system. Okay, I know I said I wasn't going to do this, but I lied. I'm going to graph these just to show you that there is no solution to this. Okay, so we have 3x minus y equals 4. And then we had, I think it was 6x minus 2y equals 4 as well. All right, let me just verify that. Okay, and 6x minus 2y is equal to 4. Okay, and so what we'll notice is that the lines are parallel to one another. They never intersect. So that verifies that they are indeed an inconsistent system. One last example. Okay, this one has a fraction in it, no big deal. So we have 1/3 x minus y equals 2 and x minus 3y equals 6. Now, our first step, and we haven't done this yet, but the first step is to multiply by a least common denominator, okay, if it contains fractions, okay? So I'm going to go back and I'm going to multiply this first equation all the way through by 3, okay? And if I do so, I get 3 times a third is going to be just an x. 3 times negative y is negative 3y. And then 3 times 2 is going to be 6. The other equation I'm going to bring over, and we get x minus 3y equals 6. And I want you to notice that we have the exact same equations. We don't even have to do anything at this point because we know that they're same equations and that they are dependent. Okay? And so the solution, I'm going to solve, it doesn't matter which one because they're both the same. I'm going to solve for y. So I'm going to subtract x, so we get negative 3y equals 6 minus x. And then I'm going to divide by negative 3. And so I would get y equals negative 2 plus 1/3 x. And my solution would be the set of all ordered pairs x, y, such that y equals negative 2 plus 1/3 x. Okay. And again, that's because we have a dependent system. Okay. There's an infinite number of solutions. If you were to graph this, you would see that that's indeed the case for this. Okay. So that's the substitution method. Okay. Substitution method works fine, except when we start getting pretty ugly sorts of equations. Okay. So there is another method that we're going to look at in the next video, and that's going to be the elimination method.